Assalamualaikum and good day to everyone. Today we continue our new topic on kinetic of a particle by using work and energy. The objective of the lecture today, number one, you should be able to describe the particle motion caused by the work of forces. And then number two, to draw the free body diagram for forces that do work as cause the particle motion. And then number three, you should be able to apply the principle of work and energy to solve the problem related to force, velocity and displacement. And then the expected outcome of the lecture, students should be able to solve problem that involve the force, velocity and displacement of a kinetic particle by using principle of work and energy. The chapter outline 10.1, the work of a force. And then 10.2, the principle of work and energy. 10.3, the principle of work and energy for a system of particle. And then we can go for example. Now, this is the summary of the lecture. So here, we study the particle motion caused by the forces. So we call it as kinetic. So under kinetic, the previous one we have studied by using the equations of motion. So you understood that the equations of motion we are using for the to calculate by using the force is equal to ma to determine the force and acceleration only. So here, by using the work and energy, we need to identify what is the work of force. So here we have three work of force. So we have first from the displacement, and then the work from the weight, and the work from the spring. So this is the equation. So now we have the work done due to the force displacement. Here the work done due to the weight, and then here we have the work done from the spring. Right. So here is the principle of work and energy. So what is the principle of work and energy? So it's given that T1 plus work done, summation of work done is equal to T2. So T is the energy. So U is represent the work done. So this is the summation. So how to determine what is the formula for the energy? So energy is equal to half mv square. Here, half mv square. So v is the velocity, m is the mass. So you must remember that this principle work and energy can only determine force, velocity and displacement. So this is the summary of the lecture. So now we go through what is the work and energy. So another equation for working kinetic problem involving particle can be derived by integrating the equations of motion. F is equal to ma with respect to the displacement. So you may see this figure. So this figure we have the particle here. So when the particle moving, we have the displacement. Okay, and then by substituting the AT is equal to V dvds into FT is equal to MAT, the result is integrated to yield an equation known as the principle of work and energy. So must remember, this principle is used for solving problems that involve only force, velocity and displacement. Also, it can be used to explore the concept of power. So before that, in order to use this principle, we must first understand how to calculate the work of a force. So number one, what is work of a force? So here, you may see to this figure, a force does work on a particle when the particle undergoes a displacement along the line of action. So if the force varies with displacement, then the work is F cos theta. So here we refer to this figure. This is the F, right? So this part from the S1 to S2, so we have F cos theta times displacement ds. So df cos theta dot ds. So word is define the product of force and displacement component in the same direction. So if the angle, so this angle in between force and displacement is theta, so the increment work done by the force is U is equal to F ds cos theta, or you can have that F cos theta dot ds. Right? Okay, so by using the definition of dot product and integrating, the total work done can be used. Okay, work done from 1 to 2 means that moving from point 1 to point 2. So it's equal to integration of f dot dr. Okay, next. Here, when we have if f and theta are constant, which is f is equal to fc, this equation further simplify to work done from point 1 to point 2 is equal to fc cos theta. So here you may refer to this figure. So when our force is equal to fc, means that we have the magnitude. So we have theta here, and then it's become, okay, the work done become fc cos theta. And then how to determine the displacement from point 1 to point 2? So we can get this displacement s2 minus s1. So you can have fc cos theta time displacement to get the displacement s2 minus s1. So here you must remember, work is positive if the force and the movement are in the same direction. So if they are opposing, then the work become negative. So if the force and displacement directions are perpendicular, the work is 0. Means that this one means that like this. So because what? Because cos 90 is become what? So that is why when the force and displacement direction are perpendicular, the work is 0. Next, the work done by the gravity. So we call it weight of an object. So you may refer to this figure. So this object is subjected to weight. So the work done here from point 1 to point 2. So we have negative w dy. So dy means that the displacement in vertical. So if we have point 1 to point 2, so the dy, the delta y, the displacement, the vertical displacement is equal to y2 minus y1. So the word of weight is the product magnitude of the particle weight and its vertical displacement. So work is positive when delta y is downward. So delta y is upward, the work is negative. Since the weight force always at downward. Right, next is from the spring force. So here, when refer to this figure, when stretch a linear elastic spring develop a force of magnitude. So we must remember that to get the magnitude is Fs is equal to Ks. So K is the spring stiffness and S is the displacement from the S transposition. So you must remember to get the S. So the deformed length minus undeformed length. Okay, to get the S. So here the work of the spring moving from the position 1 to the position 2. So we have here Fs ds. Okay, so now we understood that the spring force is equal to Ks. And then here we have the displacement. So that is what is become like this. So it have half K S square minus half K S1 squared. So this one is S2. Okay, this is the work done from the spring. So if a particle is attached to the spring, the force exert on the particle is opposite to the exert on the spring. So the work done of the spring will be negative. So you must remember the work done for the spring is negative half ks square minus half ks1 square. Okay, understand? So overall we have 3 of work done. Number 1 from the force, number 2 from the weight, number 3 if the attached with the spring. So this is the figure show that the conditions of the spring force. So here we have spring. So the force spring during the in the stretch behavior. So we have this is the ds, the displacement, and then this is this figure show the original position, means that the spring remain constant, and then this figure show the compressed spring. So this one, the first figure here is when the spring stretching, okay, and then this one when we compress the spring. So this is the ds. Alright, so the work done on spring is positive since force and displacement in the same direction. So the work done, you must remember that the half ks square minus ks square, okay, 0.1, 0.2. So here there is a important thing to remember when you are using the calculation. During the calculation, you must remember that number 1, the equation above are for linear spring only. So recall that a linear spring develop a force according to F is equal to Ks. And then number 2, the work of spring is not just spring force time distance, okay, but you must remember that times the displacement too. So it become Ks squared. Okay, in static we are using Ks only, right? So in dynamic we have the displacement. That's why it's become Ks squared. So you must beware this one. Okay. And then the third one, always double check the sign of the spring work after calculating, because the spring become positive work. Okay, if the force on the object by the spring and then the movement are in the same direction. Next, principle of work and energy. So what is the principle of work and energy? So it comes from by integrating the equations of motion. Summation Ft is equal to mat with the is equal to mv dv ds. So the principle of work energy can be written as, so the work done is equal to total energy. Okay, the which is the kinetic energy is moved from the 0.1 to 0.2. So actually it's become like this. So you may also see the video that I have attached before this teaching video from the Professor Mar maybe. So you can see that video to give more understanding on how we derive the principle of work and energy. So this actually the principle of work and energy, the total work done from initial position to the final position is equal to displacement of the kinetic energy. So this kinetic energy is come from half mv2 square minus half mv1 square. So we arrange back because this is the negative, right? So that is why we arrange to be like this. Okay, so we have the T1. So because of this one is the T2 minus T1. So here we arrange back, become like this. Okay, we have the T1 plus the total work done is equal to T2. So you must remember that T1 is the half mv square. T2 is the half mv2 square. Right? Understand? So the total work done. Okay, total work done means that the work done by all the forces. So you must identify what is the work done on the problems. Okay, acting on the particle and it moves from point 1 to point 2. So work can be either positive or negative scalar. And then must remember that kinetic energy T1 is the initial, T2 is the final position. Okay, so the kinetic energy is always a positive scalar. Okay, and then the particles initial kinetic energy plus the work done by all the forces acting on the particle as it moves from the initial to final position is equal to the final kinetic energy. Okay, did understand what is the principle of work and energy? So we are using this principle work and energy to determine what? The force, velocity and displacement only. Okay. So this is the limitation. So here, as usual, note that the principle of work and energy. So this one is not a vector. Each term result in a scalar value. And then both kinetic energy and work have the same unit. So in the SI system, we call it as a joule. So we have here 1 joule is equal to 1 Newton dot meter. So if in the FPS system, the unit become foot dot pound. And then the principle of work and energy cannot be used in general. So it is so to determine the force directed normal to the part since the force do not work. And then the principle of work energy can also be applied to a system of particle by summing the kinetic energy of the particle in the system and all the work done on the system. Okay, so now next we have the work of friction caused by sliding. So the case of body sliding over a rough surface, so we have what? We're going to have the friction. So based on this figure, let's say we have the block slides, okay, on the rough surface. So here we sketch the free body diagram. So here we have the W, right? Okay, and then we have the P here, the applied force, and then also we have the normal, and here we have the friction force. So here, consider a block which is moving over a rough surface. If the applied force just balance the resultant friction force, mu k, and a constant velocity v would be maintained. And then the equation is satisfied is P is equal to mu kn. Okay, because of the summation in x direction. Okay, however, we know that from experience, the friction generate heat. A form of energy does not seem to be accounted for this equation. It can be shown that the work term mu kn represent both the external work of the friction force and the internal work that is covered into heat. So what the application of the work and energy? So you may refer to this application 1. A roller coaster make use of gravity force to assist the car in reaching high speed in the valley of the track. So how we can design the track? What is the height of the track, the radius of the curvature to control the force experienced by the passengers. And then the next application, you may refer to this figure that we have the crash barrel are often used along roadways in front of barrier for crash protection. So the barrel absorbs the car's kinetic energy by deforming. And then if we know the velocity of oncoming car, the amount of energy that can be absorbed by each barrel. So how can we design a crash cushion? By using the work and principal energy. Okay, so this is the step for analysis. So we have 2 steps. So number 1, definitely we need to draw the free body diagram to show all the work done. So you must remember what is the work done. And then number 2, you can apply the principle of work and energy to substitute whatever information that you have. And then you must remember that the kinetic energy for T1 is the initial, T2 is the final point. So you must remember that T is equal to half mv square. And then you must remember what is the work done involved on the particle. So if you have force, so the work done is the F cos theta ds. If the particle have the weight, so the weight is weight times displacement in y. And then if the problem have the spring, so must remember that we have the half ks square. So you must remember the initial and the final point. Alright, so let's go through the example 10.1. So here we have S is equal to 0.6 meter. And then the spring is not stretched or compressed. So we have 10 kg block which is subjected to a force of 100 Newton, has a speed of 5 meter per second down the smooth plane. Determine the distance S when the block stop. So what is the means this one S? And what is the difference? So this one is the S what? 1. This one is the S2. So how to determine the S2? Okay. So we have 2 steps, right? So the first step, to draw the free body diagram to show all the work done. Okay, and then you can apply the equations of energy to determine the S2. So how you can get the S2? So you must remember that when we have the force, we need to get what is the displacement. So displacement here is S2 minus S1. So this is from this equation, you can get how to determine the S2. Right. So next, we need to draw the free body diagram to show the work done. So here, this is the free body diagram. Okay. So first, we have the applied load, right? The applied load is become 100. Okay, and then we have weight. So weight here, actually, this is the right. This is the weight. Okay. Good. This is how the weight action, the weight action on the particle. So here also we have the spring force, FR. So must remember how the spring acting to the spring. How the force acting to the spring. So here, so how many work done we have here? So we have 3, right? So number 1, we have the work done from the force of 100. So here you can have that the work done FDS is equal to 100. So ds is S2 minus S1. So you can substitute the S1 is equal to 0.6. So you have 1 here. And then the second work done is from the block weight. So you must remember that the weight times dy. So what is the dy? Dy you must resolve into the vertical here. So you substitute the W and you substitute the gravity. So you can have like this 49.05 times S2 minus 0.6. You substitute this one. Don't forget this one, sin 30. Okay, because of this is the, you must establish the what we call here, coordinate X and Y. Alright, and then the third work done is from the spring force. So the spring we have half ks square. So we understood that here the k is given to 100, and then the s is s2 minus s1. So here this is another equation. So must remember here, the spring force is not the same line of direction. So that's why become negative here. So you have total work done is 1, 2, and 3. So here, why you don't have the normal? Suppose we show the normal, right? Okay, this is because must remember that the work done, the perpendicular work done become 0. Okay, that is why not that the normal does no work, since is always perpendicular to the displacement. Okay, understand? So here you can apply the principle of work and energy. So you substitute what is the T1, what is the work done, and what is the T2. Okay, so this is the T1. Okay, this is your work done from the force. This is the work done from the W, the weight, and this is the work done from the spring. Okay, so why T2 is 0? Because we the velocity 2 is 0 because it's stopped, right? That's why we come to 0 here. So when you substitute everything here, you solve everything here, then you can solving the S2. So you select the positive root, then you get the S2 is equal to 2.69 meter. Understand?